zeta C of S is the sum over the ideals of A, integral ideals in the class of C. I'll point over the norm line. Yes, and since this is the class group is known to be finite, this is a finite sum, and it's sometimes easier to attack these particular partial zeta functions. And what Dirichlet proved in the case where k is imaginary quadratic was that the residue of each one of these at s equal 1 is the same. And it was 2 pi over the square root of the absolute value of d divided by the number of roots of unity. And that gives the residue for the zeta function, because you just sum up over the class group the residues, and so it gets multiplied by h, and that's why you get the class number formula. And we also saw that in the case of, well, in general, if you're looking at this zeta function for a given ideal class, how do we write zeta C of S in terms of something we can compute? So what we do is we choose an ideal, could be fractional J, in the class of C inverse. And then for any alpha in the ideal J, then that means that the principal ideal generated by alpha is contained in the ideal J, because J is closed by multiplication. And that means that if you divide alpha by the ideal J, that's an integral ideal. So that implies that I, which is alpha divided by J, in terms of prime factorization, is an integral ideal. Namely, the powers of each prime that divide alpha are greater than or equal to the powers of each prime that divide J. So when you take the quotient, you only get positive powers of primes. So this means ord P of alpha is greater than or equal to the ord P of J for all primes P, and this means that so consequently the ord P of I is greater than or equal to 0 for all P. And that's what an integral ideal is. And what class is this integral ideal? Well, this is in the class of J inverse, which is in the class of C. It's an integral ideal in the class of C. And moreover, we get every integral ideal in the class of C by running through the different alpha in this fixed ideal J. Just work that out. And it's not quite a bijection, because the ideal generated by alpha only depends on what alpha is up to a unit. And so we get a bijection alpha in J up to multiplication by units with integral ideals I in A in the class of C. And so if we want to sum this, which is by definition the sum over the integral ideals in the class of C, it's the same as summing over the elements alpha in J up to A star. So that shows that zeta C of S is equal to sum over a, we could say, a fundamental domain in J by A star. The units act on the ideal, so if we chose a fundamental domain, which is non-zero, and then what's the relationship between the norm of alpha and the norm of J? Well, it's here. It says that the norm of alpha is the norm of I divided, the norm of I, which is what we want, is the norm of alpha over the norm of j. So it's 1 over the norm of alpha, the norm of alpha to the s, and then we have to multiply by this whole thing by norm of I to the s power, right? Because the norm of norm of j, thank you, j, yeah. But this is just a constant, we just fixed that. So if we wanted to study this in the neighborhood of s equal 1, this is just a constant times the study of this series in the neighborhood of s equal 1. And that's how one proves the limit formula. And one shows that the residue in general of zeta c of s at s equal 1 is equal to this 2 to the r1, 2 pi to the r2, over the square root of absolute value of d, r over w. So everything but the h. And the r comes from, again, calculating a fundamental domain for the, but in the case that Dirichlet did, and that's the simplest case, a star is finite for q square root of d, when d is less than 0. And so it's much easier to do a fundamental domain. It's just, this would just be, then this sum over here would be norm of j to the s times the sum over elements alpha not equal to 0. You could just put a 1 over w here, the sum of alpha not equal to 0 in j of 1 over norm of alpha to the s. So it's much simpler. You don't have to calculate a fundamental domain. You just sum over all the non-zero elements and you divide by w because they have the same norm. Okay, and what Dirichlet never saw it in this form, but what happens is if you sum over elements in J and you choose a basis for J is a free Z module of rank 2 in this case. So J can be written as Z times alpha plus Z times, I'm choking over the alphas, so let's do it. Z beta 1 plus Z beta 2 in the case of d squared of minus d. Squared of d. And therefore, an element alpha is of the form x beta 1 plus y beta 2. And if you calculate the norm of alpha and you divide it by the norm of j, because you have to pull this out, so the norm of alpha divided by the norm of j turns out to be a binary quadratic form in x and y, the form ax squared plus bxy plus cy squared. And so this series becomes a classical series that Dirichlet studied series is of the form 1 over ax squared plus bxy plus cy squared to the s power. And these are the series that he used to prove the class number formula. And I also did an example. So today we're going to prove another formula in the imaginary quadratic case because we also know that zeta k of s is the Riemann zeta function times L of chi s, where chi is a character of z modulo the discriminant, plus or minus 1, and this is the famous quadratic reciprocity formula. So we're going to prove a formula for L chi of 1, which is the same thing as the residue of the zeta function at 1, because the residue of the zeta function here we saw was 1. So the residue of zeta s, zeta ks, is equal to the value of L chi 1. And what Dirichlet is going to prove a beautiful formula for it, which turns out to be minus pi over the square root of the absolute value of d, the sum from a equal 1 to d of chi of a times the rational number a over d. And it's important you go from 1 to, I mean, this only depends on a mod d, but this really depends on a. So these are just plus or minuses a over d. And when you combine that with the class number formula, you get a beautiful formula for h. And I was trying to do that formula and compute it for you in a case of 23. So the formula for h is, so what we're going to do in the case where d is minus a prime, where L is 3 mod 4. And then the formula is that, it just is 2H over W when all the smoke clears is minus the sum from A is equal to 1 to L of chi of A, which is just the quadratic residue symbol of A, times the rational number A over L. So you could not ask for this is just a plus or minus 1. And so it's the sum, so it's 1 over L, the sum over the non-residues of A from 1 to L, minus the sum over the quadratic residues of A. And I wanted to illustrate that for you in the case of L equal 23. So we're going to prove this formula today. The formula, the analytic formula for the L series of 1. And I was trying to illustrate it for 23 and got all boggled up with the calculation of quadratic residues and non-residues, so let me at least do that intelligently. How does one make a list if you go from 1 to 22, which are the quadratic residues and which are the non-residues, right? Okay, so here are the quadratic residues, here are the non-residues. Well, what you have to do is you have to figure out for the primes less than 23, whether it's a residue or a non-residue, right? So I said 1 is always a residue, 2 is a residue, and 3 is a residue. So again, you have to do quadratic symbols. And then 5 is a non-residue, and as someone pointed out, 7 is a non-residue, and also 11 is a non-residue. Okay. So once you've done that, you can fill in the table, because when you multiply quadratic residues, you get quadratic residues. You multiply non-residues, you get a quadratic residue. You multiply a quadratic residue times a non-residue, you get a non-residue. So for example, from this, you deduce that 4 is a quadratic residue. And then you deduce that 6 is a quadratic residue. And then you deduce that 2 times 4, which is 8, is a quadratic residue. And then you deduce that 9, which is 3 squared, is a quadratic residue. Right? And then also 12 is a quadratic residue, etc. Now how about here? Well, since 2 is a residue and 5 is a non-residue, that says that 10 is a non-residue. We also know that 11 is a non-residue. So we've now got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 figured out. Okay, now we use the fact that minus 1 is not a residue because 23 is congruent to 3 mod 4. So minus 1 is a non-residue. And so if you have these quadratic residues, their negatives have to be non-residues. And if you have these things, the negatives, so you can go from there. And it turns out that you get 13 and 16 and 18. And that's all the quadratic residues. This is minus 10, this is minus 7, and this is minus 5. And then you take all the negatives of these guys, and you get the non-residues, which are 14, 15, 17, 19, 20, 21, and 22. This is minus 1, minus 2, minus 3, minus 4. This is minus 6, this is minus 8, and this is minus 9. Good? Okay, now let's see what happens when we sum up the non-residues. So when you sum up all of these numbers, and you do it quietly in your own room, so you actually do it correctly, you get the sum over the non-residues is 161, which you check is 7 times 23. It always has to be a multiple of 23. And the sum over the quadratic residues, which is smaller, turns out to be 92, which is 4 times 23. So if you take this minus this and you divide it by 23, you get 3, which is the class number, amazingly enough. So it worked. But but you can see this isn't so efficient, because to do this, you have to calculate these symbols up to L over 2. I mean, these things are given to you, but you have to know whether to take them plus or minus up to 22. Nonetheless, already this formula is pretty good, because, well, usually the number of roots of unity is 2. I mean, if L is greater than 3, W is equal to 2, so it's an actual formula for the class number. Let's see what it says about the parity of the class number, whether it's even or odd, right? Here it turned out to be 3. Well, if I just cared about the parity, it would say H is congruent mod 2 to 1 over L, the sum over all the things. I mean, I just put a plus sign here, I have the same parity, right? I mean, I'm only dividing by something which is invertible mod 2. So it would be the sum over everything of A. A is equal to 1 to L minus 1, right? Well, this sum is L minus 1 times L over 2. I divide it by L. I get L minus 1 over 2, right? L is congruent to 3 mod 4. So that's an odd number. So it says that for all these primes congruent to 3 mod 4, and for L equal 3, the class number turns out to be 1, the class number is odd. And in fact, Gauss proved, I better leave that up because I'm going to prove that. So while we're on the subject of class numbers, Gauss, when he investigated binary quadratic forms, so he made tables of class numbers, he noticed that that was basically the only time the class number was odd. So Gauss, H is odd if and only if D is a prime power. So remember, the discriminant is basically square free. So the only way D can be a prime power if it's negative is minus 4, minus 8, or minus L for these L. In these two cases, the class number is 1. And more generally, Gauss proved that if you took the class group and you divided by 2 times the class group, so that's an elementary abelian 2 group. So this has order 2 to the t minus 1, where t is the number of prime factors of D. That's called genus theory. That would also be a good subject for a paper. And so that's a refinement of this, because this is the case where the number only has 1 prime factor, so the class number, so this group is trivial, and that means that the class group is odd. Now you might think this is a curious statement, but in fact, this has been used as a primality test. I mean, it sounds ridiculous. But you take some enormous number, which is congruent to 3 mod 4. And you're interested, is this number prime or not? Well, if you could calculate the class number of the associated imaginary quadratic field, and you could determine whether it was even or odd, that would tell you whether the number was prime or not, right? You might think, well, good God, it must be awfully complicated to calculate. Why don't I just, but it's much faster than dividing by the numbers less than the square root of the prime. And the way people like Shanks, I mean, people have become incredibly clever at these primality tests. So what they do is they take an ideal. So they study. They want to test some number n, which is congruent to 3 mod 4. Is this prime? So they study q squared minus n. They take some ideal in q squared minus n, which they actually think of in Gauss's notation as a binary quadratic form. It's actually easier to do this. And they calculate the order of this ideal in the ideal class group. And they just keep multiplying it by itself, which is composition of this binary quadratic form, until they get a principal ideal. And typically, that's the order of the class group. Because if you just grab a random abelian group, it'll be cyclic. And if you grab a random element in that abelian group, it'll be a generator. So they take a random ideal and just take its power and see if it's and they conjecture that the first power of it, that the principal is the order of the class group, and if that turns out to be an even number, for example, you're not prime. Isn't that clever? Yeah, I mean, it's incredible how they use these deep theorems in number theory to do things like primality testing. But anyhow, let us leave that aside and see if we can prove this beautiful formula for the L function of 1, because it's completely analytic and it really has nothing to do with number theory at all. I mean, Dirichlet takes as definition for this the sum of chi of n over n greater or equal to 1, n prime to d. This is a conditionally convergent series, and he's going to tell you what its limit is. So we forget ideal classes, we forget all that kind of stuff, and we just do a little analysis. So to do this, I have to introduce Gauss sums, and we're going to need Gauss sums anyhow, because we're going to get to the proof of the functional equation of these L functions, and that involves Gauss sums in a big way. So Dirichlet had a way of rewriting this sum using Gauss sums and the logarithm function, and I'll show you that. So I'm going to restrict, because it's a little easier for my, exposition, but it works in the general case. I'm going to do Dirichlet. This again has nothing to do with the character being quadratic. This is a true formula for all the characters chi of z mod d star to c star in that analytic sense. But I'm going to assume that d is a prime. It's a little easier for me. Not necessarily at 3 mod 4, just a general, the modulus is a prime. And I'm going to assume that the character chi from z mod L star to C star is non-trivial. So in general, if you did it characters of z mod D star, you'd have to assume they're primitive, namely they don't come from some conductor dividing. All right? All right, so we know what L of chi s is, and I'm going to define the Gauss sum of chi associated to this non-trivial character. Well, it's the sum over the A mod L of chi of A, the value of this, which is some root of unity, L minus first root of unity, times e to the 2 pi I A over L. So it's a sum of roots of unity. This is an L minus first root of unity, and this is an Lth root of unity. And you multiply those two, you get a root of unity, and then you sum that over these L minus 1 classes. We don't take A equals 0, or if we do K, non-zero. And both of them depend only on what A is mod L, because this is an element in here, and so it depends only on what A is mod L, and this also depends only on what A is mod L. Okay. So I'm going to prove, Gauss proved a nice lemma about these, a fundamental fact, that if you take the product, first of all, it's not even a priori clear that this is non-zero. You're just summing up roots of unity, and you just get an algebraic integer. This is an algebraic integer, because roots of unity are algebraic integers, but it's not clear it's non-zero, but it is non-zero. Gauss proved the formula that g of chi times g of chi inverse, and that, remember, that's the same as the character chi bar, that's equal to chi of minus 1 times L. And since this is non-zero, both of these have to be non-zero. Another way of writing it, if you calculate g of chi bar, the complex conjugate of g of chi, what is that? Well, that's the summation of chi bar of A e to the minus 2 pi I A over L, right? Because the conjugate of this is you get the inverse root of unity, right? And that is, if we replace A by minus A, so the sum over A, it's the same as the sum over B, which is minus A, you could do it that way, of chi of B, chi bar of B, chi of minus 1, chi bar of minus 1, because that would be chi of A, and then this would be e to the 2 pi I B over L, right? And that's the Gauss sum of chi bar times chi of minus 1. So the complex conjugate is the Gauss sum of the inverse character times this number, and therefore we see that g of chi, another way of saying Gauss's theorem, is that the complex number g of chi, if you multiply its conjugate, it has absolute value L, or the absolute value in the usual sense of complex numbers is the square root of L. Okay? Okay. Now, if chi is, if we're in the situation that Dirichlet was particularly interested, where chi inverse is equal to chi, i.e. chi squared is 1. So if we're in the situation where chi is quadratic, this says that the square of the Gauss sum is plus or minus L. Well, it's L if L is congruent to 1 mod 4, and it's minus L if L is congruent to 3 mod 4. That's the quadratic case. It gives you the square of the Gauss sum. Now, a huge amount of effort was spent by Gauss and Dirichlet figuring out what the sign of it was, and that's actually going to be important. See, I mean, this is a well-defined complex number, and we know here that its square is L, or minus L, but what is the number? I mean, there are 2 square roots of L, and there are 2 square roots of minus L, right? So the sign turns out to be, and this is a much harder result than what I'm going to prove. I'm going to prove this for you, or at least wave my hands at it. The sign of the Gauss sum, it turns out to be, in the quadratic case, it's the positive square root of L for L congruent to 1 mod 4, and it's I times the positive square root of L for L congruent to 3 mod 4. So it tells you which exact square root it is. By the way, this is really an important result, because what it shows is that when chi is quadratic, you see all these numbers are plus or minus 1. And so you're just taking a sum of Lth roots of unity. So you're in the Lth cyclotomic field. You're an algebraic integer in the Lth cyclotomic field. So why would you expect this? Because the Lth cyclotomic field is an extension of Q where the Galois group is Z mod L star. And your Gauss sum of a quadratic character turns out to be in this cyclotomic field. How does the Galois group act on it? Well, if you're a quadratic residue, you don't change the Gauss sum. If you conjugate this by, all right, so let's do that. Getting a little bit taken afield here, but let's keep up Gauss's formula and let's go to the case where we're quadratic. So chi is equal to 1 on A. Yeah, so what does the Gauss sum look like? G of chi looks like the sum over the quadratic residues of e to the 2 pi I, well, let me just write it as zeta to the A, minus the sum over the non-residues of zeta to the B, where zeta is equal to e to the 2 pi I over L, is the generator of this. Correct? Okay. Now suppose I act on this. This Galois group is isomorphic to Z mod L star by an element C in this. The Galois automorphism of zeta takes it to zeta to the C. So suppose I apply sigma C to G of chi. Okay? I replace this by AC. Well, if it's a quadratic residue, I get the same sum. It's just I'm ordering the elements in the term differently, and I get the same non-zero. So this is equal to G chi if C a quadratic residue, and it's equal to minus G chi if C is a non-residue. Okay? So over this subgroup, which is of index 2 in Z mod L star, I have some subgroup of which are the squares, and I have some fixed field here, K and Q, and this is the full Galois group. If I sum over this subgroup, the element G chi is fixed. So by Galois theory, G chi actually lies in this subfield. And if I take a non-residue, which generates the Galois group of this quadratic extension, it's taken to its negative, right? So if you write this field as K is Q plus Q square root of something, I don't know what it is, but it's a quadratic field, then it says that G of chi lies in this one-dimensional subspace, because that's exactly the things that are taken to their negative. It might be 0, but if it's non-zero, it tells you what n is. And you see, this formula that Gauss found tells you what that quadratic extension is inside the cyclotomic field. In the case L is congruent to 1 mod 4, it's the quadratic field square root of L. And when it's congruent to 3 mod 4, it's this quadratic field minus square root of L. And that's the first example of explicit class field theory for the rational numbers, because quadratic fields are abelian extensions of Q, and they're supposed to be contained in a cyclotomic field. And this formula of Gauss tells you which cyclotomic field it's contained in. And you see, it's perfectly set up to behave in a certain way under the Galois loop. Okay, so now let's see how you prove Gauss's lemma from this definition and everything. So it's the beginning of what we're going to see as Fourier analysis, which we're going to use a lot in the functional equation, etc. Let's set it up properly. Now, as I said to you, Fourier analysis, you start with a function on some abelian group, and then you get a function, the Fourier transform, on the dual group. So we're going to do Fourier analysis on G, which is the cyclic group of order L, under addition. Okay? Now we saw when you had a cyclic group of order L, the dual group was the Lth roots of unity in the complex numbers. Because a character, you have to say where you took the class 1 mod L, and it could go to any Lth root of unity. Right? But in the theory of Gauss sums, we're going to identify the dual group with the original group, because we can if we pick a generator of the Lth roots of unity. And we're going to always pick as generator, because we're over the complex numbers, zeta, which is e to the 2 pi I over L. Now, okay, that's you can't do that algebraically. You know, if you're just given the Lth roots of unity, you give the Lth roots of unity, there's no generator. But in the complex numbers, there's a generator, the point that's closest to 1. Okay? And so in that case, this is isomorphic to Z mod LZ, where an element B here corresponds to the element e to the 2 pi IB over L, because the element 1 corresponded to this. So therefore, if you have a function on G, its Fourier transform under this identification becomes another function on G. So if f is a map from G to C, then f hat is a new function on G, and it's defined by this. Well, maybe I changed a little notation, but this is close to what I call the Fourier transform. Right, from A mod L. So you take the values of the function, you multiply them by the values of the character. This is basically chi sub B inverse of A, right? The character takes, B is associated to the character that takes 1 to this root of unity. And therefore it takes A to this root of unity, So previously, you remember you had a Fourier transform which was defined on characters by summing the element times the value of the character. So when you make this identification, it just becomes this sum, which now, that's all very well for a function. And what we're going to do is we're going to calculate the Fourier transform of chi. Chi is a function from Z mod L to the complex numbers. It takes 0 to 0, and it takes other things, A not equal to 0, to chi of A, which is multiplicative. So this is a weird abelian group that contains a subset which is a group under another law. And in general, if I had a field, I'd have the same thing, right? I mean, Z mod L is a field. If I had a field, that gives a very simple additive group, but inside the field, I have the multiplicative group. And as functions on the field, I could take a character of the multiplicative group and extend it by 0 on the 0 element. And that's going to happen a lot as we're going to do the functional equation. And so this isn't calculating the Fourier transform of anything, but we're going to calculate the Fourier transform associated to a character of Z mod L star. Okay, let's do it. Let's figure out what it looks like. And then we'll get Gauss's lemma out of Fourier duality. Well, what is chi hat of B? Under this definition of F hat, well, it's the sum over A of chi of A e to the minus 2 pi I AB over L. That's the definition. It's a function now on B. Okay, now let's do the case when B is equal to 0. If B is equal to 0, all of these are 1, right? So it's just the sum over the character of values on A. The value on A equals 0 is 0. And when you sum over the non-zero elements, and we're assuming that we have a non-trivial character, I should have said that many times, chi not equal to 1, all right? The sum of the non-trivial values of the character is over the group is, of a non-trivial character over the group is 0. So this says that this is equal to 0 if B is equal to 0, right? As sum over A not equal to 0, chi of A is equal to 0. Okay, now if B is not equal to 0, then I claim it's equal to the sum over C, which is minus A times B. So instead of summing over A, I multiply everything by minus B. And that's an automorphism of the this is really just sum over A non-zero because chi of 0 is already 0. So if B is non-zero, instead of running through the non-zero classes, I multiply them by minus B and run through them this way. And then chi of A becomes chi of minus C over B, right? Because A is minus C over B. And this is minus AB, that's e to the minus 2 pi I C over L. Okay? Now,
should be just 2 pi C, because I have this negative AB.
Thanks, 2 pi I C, thank you. Perfect. Good. Now, this B is a constant. This is B not equal to 0. So we can pull out chi inverse of B, and we can pull out chi of minus 1. So this is the same as chi of minus 1, chi inverse of B. And then what are we left with? The sum over C, chi of C, e to the 2 pi I C over L. And this is what we call the Gauss sum of chi. Right? That was the definition of the Gauss sum of chi. So we see what chi hat is. So we don't do a Fourier transform of a general function, we do a Fourier transform of a character, and we find that chi hat is equal to a constant, namely chi of -1 times the Gauss sum of chi times chi inverse. Namely, this is just a constant, and that the function defined by the Fourier transform is just the inverse of the character times this constant, right? Because the inverse of the character takes value 0 when b is equal to 0, and it takes value chi inverse of b. That's the only thing that depends on b here. So Gauss sums come up as sort of the multiplicative constant that happens when you do Fourier transform. You don't quite get the inverse character. You get the inverse character times this constant, which strongly suggests that this is non-zero, because if this turned out to be 0, the 0 function, we're supposed to be able to recover the function from its Fourier transform. The only thing you can recover from the 0 function is 0, right? So, and in fact, that's what Fourier duality says. So if this is the formula for chi hat, what's the formula for the Fourier transform of chi hat? Well, it's the Fourier transform of this. I mean, Fourier transform is linear times this. So I get chi of -1 g of chi times the Fourier transform of that, but that's the same thing. So that's times chi of -1, chi inverse of -1 times g of chi inverse times the character chi, right? I mean, this is the Fourier transform of chi inverse by the same argument. And notice that the value of this at -1 is the same as the value of this at -1, right? So they cancel. So I get that the Fourier transform is equal to g of chi times g of chi inverse times chi. And if you remember Fourier duality, you almost recover the function from its double Fourier transform. There's some issues of measure, and when you work out the measure, you get a function like this. So I will, the exact formula for double Fourier transform is that f hat is equal to of A is equal to L times f of minus A. This L comes in, as I said to you, you have two different measures on the cyclic group of order L. You have the measure as a discrete group, which gives every point volume 1, and you have the measure as a compact group, which gives every point volume 1 over L, and you have to use both of those measures in Fourier transform. So this is the general formula for duality, and when you plug that in, you get this formula. You can also prove this directly. Gauss didn't have the theory of Fourier duals and anything like that, but this is somehow what's going on behind it. Okay, so now let's use this formula for Gauss sums to rewrite this series that Dirichlet wants to sum. Okay, so consider the following. If we multiply if we take g of chi inverse and we multiply by the value chi of n, what do we get? Well, g of chi inverse is by definition the sum from a equal 1 to L of chi inverse of a e to the 2 pi I a over L. And then we multiply that by chi of n. Okay, and then we bring the n inside, and we write this as the sum from b is equal to 1 to L, where b is a over n. So this is, again, n prime to d, n prime to L. We write b is equal to a over n, and that makes sense, we can divide by n. And we get chi inverse of b, because I have a chi of n and a chi inverse of a. And then I get e to the 2 pi I bn over L. Okay? Where here again, it only depends on what n is mod L. Well, that's good, because I'm going to use that to rewrite the whole Dirichlet series. So now consider g of chi inverse times L chi of S. So that's the sum from n equal 1 to infinity, n prime to L, of g of chi inverse, chi of n over n to the S. Right, I just bring the g of chi inverse inside. And then I use this formula for g of chi inverse chi of n. Right? So I write this now as equal to the sum from b is equal to 1 to L, chi inverse of b. And then I have the sum from n equal 1 to infinity. This is an infinite, this is a finite sum. And sum from n equal 1 to infinity, n prime to L, of e to the 2 pi I bn over L. And divided by n to the S. You'll see what the madness is in this in a minute. So I've rewritten the Dirichlet series. Instead of summing over the chi's, I just have these Lth roots of unity over n to the S, where the Lth root of unity depends on n. And then that's an infinite sum, and if I can evaluate that, then I multiply it by chi inverse of b, and sum goes up as a finite sum, and I get this quantity. Okay, what's so good about that is now we put S equal 1, and we see what we get. So g of chi inverse L of chi 1 is equal to, well, we have this sum, chi inverse of b. And then we have the sum, conditionally convergent, e to the 2 pi I bn over L divided by n. Now what does that look like? Well, I claim, let's rewrite this as e to the 2 pi I b over L to the nth power. So that's the sum of t to the n over n. The absolute value of t is less than 1, or equal to 1. So that's the series for the logarithm. And that's what remember, we have the log of minus the log of 1 minus t is the summation of t to the n over n, which works for t less than or equal to 1, t not equal to 1, and these are non-trivial roots of unity. Okay, so we rewrite this as the sum over b, a finite sum, chi inverse of b, times the log of, well, 1 minus e to the 2 pi I b over L, with a minus sign out there. Minus summation of chi inverse of b, the log of 1 minus zeta to the b, where we're taking the principal branch of the logarithm, right, which converges on a disk, goes from 0 to a disk around 1. Okay. Okay. Good. I seem to have missed something here. Okay. So, that's formula for this. If we want L chi of 1, I'm going to use the fact that G of chi times G of chi inverse is equal to chi of minus 1 times L. And I'm going to divide both sides by G of chi inverse. So I get rid of this. I have a 1 over G of chi inverse, and I replace it by the formula I get here. So I have finally the formula. Analytic formula. And then we're going to torture that. 1 over, minus G of chi over chi minus 1 times L, because I divided by G of chi inverse. L chi 1 is equal to this, times the finite sum, B is equal to 1 to L of chi inverse of B, the log of 1 minus zeta to the minus B. So zeta to the B. There we go. Okay. Now, we're going to restrict to the case where chi squared is equal to 1 and chi of minus 1 is equal to minus 1. That means the imaginary quadratic fields. Quadratic fields, q squared minus L. Okay. Well, there are a lot of simplifications that occur. First of all, I'm going to need the sign of G of chi. So the sign of G of chi is I times the square root of L. So then this becomes minus I square root of L, positive square root of L, divided by, this is minus 1 and this is L. So minus L. And then chi inverse is the same as chi, so it's just chi of B, which is a plus or minus 1, right? Times the log of 1 minus zeta to the B. Okay, now the logarithm is a complex valued function. It has a real part and an imaginary part, right? The log of 1 minus z is equal to the log of the absolute value of 1 minus z, that's the real part, plus I times the argument of 1 minus z. Okay, now, I claim that if you write this as a sum of its real and imaginary parts, the sum over the real parts is 0. And the reason is that the log of absolute value of 1 minus zeta to the b is exactly the same as the log of 1 minus zeta to the minus b. I mean, this is the complex conjugate of that. And so you get the same real part for b and minus b, but on the other hand, chi of b is minus chi of minus b. So this is multiplied by minus, and so these two things cancel out. Isn't that nice? So we're down to the argument. Yay, all right. Let's divide here. We get, let's see if I did this right. Yeah, we get I over the square root of L, positive square root of L, times the sum of chi of b times the argument. Well, there's an I again. Where's the I times the argument? So I get an I squared here, times the argument of 1 minus zeta to the b. And to finally get this formula, this is of course a minus 1 over the square root of L, we have to work out what the argument of 1 minus zeta is. So that's a nice exercise. I don't want to ruin your lunch. Let's see what we're doing here. Plenty of time. Let's do the argument of 1 minus zeta to the b, and we'll get our final formula. If you didn't have the sign of the Gauss sum, all you'd have here is plus or minus. You wouldn't know whether it was plus or minus. Okay, we write 1 minus zeta to the b as zeta to the b over 2 times zeta to the minus b over 2 minus zeta to the b over 2. Okay, b is running from 1 to L. So b over 2 is running from 1 to L over 2. So this number has argument between 0 and pi. And 0 is less than the argument, which is equal to pi b over L, which is less than pi, for this number. Okay, what about the argument for that number? Well, this is a purely imaginary number. If you take its complex conjugate, it goes to its negative of itself, and you find that its argument, it's either positive, it is minus pi over 2, if I did it right, because this one came first. And so when you just add the arguments, you find that the argument of 1 minus zeta to the b is minus pi times b over L sorry, it's plus pi times b over L minus a half. And when we sum over the character chi of b, it's a non-trivial character. So if you sum the non-trivial character times the minus a half, you get 0. It's a constant times the sum over the non-trivial character. So this whole thing becomes minus pi over the square root of L, the summation over b of chi of b times b over L. The rational number b over L. And that's it. Is that what I said I was going to do here? Yeah. And this is the case, b is equal to L of this formula. You put it all together, you get that amazing formula for the class number. Well, you can see, this is all work that Dirichlet did. He calculated the residue of the zeta function in the imaginary quadratic case. He calculated the value of the L function. He proved this identity. All of this was work he was doing on his own. And no one else was thinking about L functions except for Dirichlet. But then, Dirichlet's work created a sensation. And the next great paper, which we're going to discuss when we leave now the work of Dirichlet, is the work of Riemann. So Riemann wrote a great paper in 1859. It's the only paper he wrote in number theory. And in that paper, he proved two things. One, he proved the functional equation of the zeta function, and his methods work just as well for Dirichlet L functions, and we'll do that. And the second thing was he speculated on the zeros of zeta of S. They thought of as a meromorphic function on the entire complex plane. And that's going to involve Fourier analysis and the Gauss sum. So he borrowed a lot of Dirichlet's methods. The methods were all there, but Riemann put them together. And I'll do a little bit of two, but I'll start next time with the beginning of the proof of the functional equation. Okay? And then, after we do Euler and Dirichlet and Riemann, we'll jump into the 20th century and see what's happened to all these things under the work of Hecke and Artin and others. And maybe it'll be more coherent. Okay? See you on Thursday. And let me know if I'm going too fast or going too slowly. I'm relying on the faculty here to tell me if I'm going too fast. So if the faculty tell me I'm going too fast, then I'm probably going too fast.